All right, welcome back. So this is the third lecture on the series of eigenvalues, eigenvectors, and how to solve systems of differential equations. This is one of my absolute favorites because this is where it all comes together. So I'm staying late just for this lecture. In the last few, we have talked about why we have, these systems of ordinary differential equations, x dot equals ax, x is a vector, a is a matrix, and these dynamics are coupled. But it's a lot easier to solve this system of equations if A was a diagonal matrix. So we try to find a coordinate transformation, some matrix T, some invertible matrix T, into some new coordinate system Z, so that Z dot equals a diagonal matrix Z, because this is way, way easier to solve this system where D is diagonal and the dynamics are decoupled than this system here where A is not diagonal. And specifically, we derived the eigenvalue eigenvector equation for the t's and the d's where this is possible. Specifically, a times t equals t times d. This is the eigenvalue problem. Columns of t are eigenvectors of A. The diagonal elements of D are eigenvalues of A. So the coordinate transformation that diagonalizes A are specifically the matrix of eigenvectors of A. And the D, the diagonal system that you get after doing that, these diagonal entries of D are the eigenvalues of A. Good. So I think I want to just show a couple of things. I'm going to do a little bit of Python Matlab demonstration here just to convince you that yes, in fact, D equals, what did I have? T inverse A T is true. And also conversely that if I had D and T, that A would equal T times D times T inverse, okay? And it's really, really, really easy to compute eigenvalues and eigenvectors in MATLAB and Python, so I'm just gonna show you that real quick. And then what I'm gonna do, kind of the culmination of this set of lectures, is I'm going to assume that we've gotten we've decomposed A into its eigenvectors T and its eigenvalues D. So, however means, Python or MATLAB, we started with A, and we solved for T and D. And then I'm going to show you that with those matrices, I can solve my original system of equations up here. So this is like my favorite lecture in differential equations so far. And so I'm just going to show you right now. So the first thing I'm going to do is I'm literally just going to confirm, in fact, that it's easy to get eigenvalues and eigenvectors. I guess I'm going to start in MATLAB. So I'm creating an A matrix 0, 1, -2, -3. And all I'm going to do is get its eigenvectors T and its eigenvalues D using the eig command, the built-in eig command. So it's literally one line to get all of the eigenvectors and all of the eigenvalues. So I'm just going to run that. And so T are eigenvectors 1, okay, so it normalizes them so that they have length 1. So if you take, this entry squared plus this entry squared, it'll have length 1, same with this. But essentially you can think of this as, the 1, -1 direction. And this is the, I guess it looks like the -1, 2 direction. And what I'm going to confirm for you, and then our eigenvalues are -1 and -2. So I'm going to confirm these two expressions here. So if I take inv of t times a times t, that had better equal my diagonal matrix. And yes, in fact, it does, -1, 0, 0, -2. And I'll confirm the other one, that if I take t times my diagonal matrix times the inv of t, that should equal my original A matrix. And in fact, it equals 0, 1, -2, -3. Good. Quick sanity check. It's real easy to get eigenvalues and eigenvectors, one line of MATLAB, and these properties that we think should hold do in fact hold. Let's just do kind of similar things in Python. Here, again, you can import numpy as np. I actually don't need these other ones. This is just from another script. So I'm going to create an array, the same array, 0, 1, -2, -3. And it's just as easy to get eigenvalues and eigenvectors. It's just, from np lin alg, it's again the eig command. So just eig of A, and it spits out eigenvalues and eigenvectors in these structures. So I'll just run this, run, and it printed out the eigenvalues. If I want to, what's happening? If I want to print the eigvecs, that should also work. And again, it is normalizing them to be unit norm. So you can define your eigenvector. Any vector along an eigenvector direction is technically an eigenvector. We usually pick the convention that our eigenvector has a unit length. That uniquely determines it. Okay? And these are the same as before. And so clearly these are also going to hold. Good, that's all I wanted to show you in code. So now what I'm going to do is we are going to use these diagonal matrix D and these eigenvectors T to solve our differential equation. Okay, and so we know that it's quite easy to compute. It's easy to compute the solution of this. This is just z of t equals e to the matrix D times whatever initial conditions I have. I should probably write down my initial conditions. I have, x at time 0 are my initial conditions. And those initial conditions are going to, have a corresponding initial condition in z. This is literally z naught is t inverse x naught. That's pretty simple. And we're used to thinking that the solutions of differential equations x dot equals lambda x. If I had x dot equals lambda x for a scalar x and for a number lambda, and I had some initial condition, then the solution would be x at time t equals e to the lambda t times my initial condition, e to the lambda t times x naught. And so here I'm guessing that I get something similar, that x, my vector x at time t, is probably going to be e to the matrix A times time times a vector of initial conditions. Okay? Now the question is, how do I compute this matrix exponential? I haven't shown you how to do this. So that's kind of one of the things I'm going to show you in this lecture is how do you compute this matrix exponential, and how do you use t and d to make it really easy to compute this thing. Okay, so I shouldn't have erased all of my stuff. So we know that A is equal to t d t inverse. What do I want to do here? I want to tell you that this matrix exponential, sorry, I'm skipping a step here. This matrix exponential e to the a t, and I'm going to drop the under bars. We know that A is a matrix. I told you before that you can take the power series expansion for the exponential e to the x, and you can substitute in this matrix AT every time you see that variable x. So the power series expansion of exponential says that this should be, I'll write e to the x. So e to the x is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, 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 dot. And so this is going to be a matrix. This isn't going to be a scalar. So instead of 1, it's going to be the identity. And instead of x, it's going to be, I'm going to substitute in AT every time I see an x. So plus AT plus a squared, t squared over 2 factorial plus a cubed, t cubed over 3 factorial plus dot, 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 dot forever and ever and ever. Now, computing these matrix powers is going to get pretty tedious pretty fast. Like matrix multiplication is not cheap for big matrices, so I don't want to be actually computing all of these matrix powers. And so I'm going to use T and D and special properties of those to make it really, really easy to compute these things. That's kind of what I'm going to show you now. Okay, so we already know that A equals t d t inverse. That's fine. We computed this using, the eig command in Python or Matlab. And now I can write that A squared, this is where it gets pretty fun. A squared is just this thing times itself, so it's t d t inverse times t d t inverse. But notice that I have a t inverse times t. So these actually cancel out. And this equals t times my diagonal matrix squared times t inverse. And this is actually not so bad to compute. D squared is easy. I just square all of the diagonal entries, right? Like a diagonal matrix times itself. A diagonal matrix squared is just the square of the diagonal entries. Okay, it's another diagonal matrix where the entries are squared. So this is actually easier to compute. Similarly, we can compute A3, A cubed. That is t d t inverse times t d t inverse times t. I hope you're seeing the pattern here, t inverse. Again, all of these in the middle cancel, and I'm left with t d to the third power t inverse. Again, this is really easy to compute d cubed. That's just a diagonal matrix with all of the entries of d cubed. So that's nice. And I can do this kind of ad nauseum if I wanted. Dot, dot, dot. A to the power n, the nth power of a, is just going to be the same exact thing. It's going to be t d to the power n times t inverse. And so basically every single term in here, whenever I see an a or an a squared or an a cubed or so on and so forth, I can plug in these expressions in terms of its eigendecomposition, in terms of its eigenvectors and eigenvalues. Sometimes I call that its eigendecomposition. This is the eigendecomposition of a. And I'm going to use one more fact, which is that this identity I can be written as t times t inverse. Okay, that's all we need to write this down. So what I'm going to write is that this expression here equals, maybe I'll use pink since most of these here are pink. So this equals t times t inverse plus t times d times t inverse little time plus t times d squared times t inverse little time squared over 2 factorial plus t times d cubed t inverse little time cubed over 3 factorial plus dot, 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 forever and ever and ever. And now what I can do is I can say that every single term in this has a big T on the left and a big T inverse on the right. This scalar thing, I can move that anywhere because it's just a scalar. So the matrix part of this has a big T on the left and a T inverse on the right for every single term in this expansion. And so that equals big T times identity plus dot, 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 a bunch of stuff times T inverse. And this is the stuff inside is the identity plus a diagonal matrix T plus a diagonal matrix squared, T squared over 2 factorial plus a diagonal matrix cubed, T cubed over 3 factorial plus dot, 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 dot. And now you'll see, so like if that was too fast, just pause and convince yourself that this equals this. I literally just popped this big T on the left from all of these, and this big T inverse on the right from all of these, and then I collected all the stuff in the middle, identity, big D times T, big D squared, T squared over 2 factorial, D cubed, T cubed over 3 factorial. And now, all of the stuff in the middle is actually really, really easy. All of the stuff in the middle is the power series expansion, the representation of E to the diagonal matrix T. But we know that this is actually really easy to compute. All of these matrices, all of these powers of D are just still diagonal matrices. And so to get this E to the power matrix D times T, this is literally just a diagonal matrix, you know, E to the lambda 1 T, e to the lambda 2t dot 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 with zeros everywhere else. I can just write this matrix exponential down for this diagonal matrix. I don't even have to compute this. This is just, I can write this down. Okay, it's a diagonal matrix with e to the lambda t's. And so now I hope you're seeing that instead of computing this infinite set of powers of A, which is going to be heinous to do, now all I have to do is compute the eigendecomposition. I get t and d. I compute e to the dt, and I multiply it on the left with big T and on the right with big T inverse. And that is my solution. My solution, x at time t. I'm going to write this down. Maybe I'll write it down in green. X at time t is equal to big T e to the diagonal matrix times time times big T inverse, that's e to the at, all of this is e to the at, times x naught. Okay, this is the solution. This is the solution to x dot equals ax with this initial condition x naught. Okay, so this is a big deal. We had this original differential equation that was really hard to solve. Maybe I could have, guessed that this is the form of the solution, but still, how do I compute this matrix exponential? This is going to be a nightmare to do for a generic A matrix. So instead, what we do is we think, well, it would be a lot easier if this was diagonal. So let's find a coordinate transformation into a coordinate system Z where my dynamics are diagonal and decoupled, so I know how to solve that easily. It's easy to compute e to the diagonal matrix T. I do that by finding my eigenvalues and eigenvectors of this A matrix. So my eigenvectors T, my eigenvalues D. And then I also find that those eigenvalues and eigenvectors make it much, much easier for me to compute this matrix exponential. I can kind of write, every time I see an A matrix, I can write it in terms of its eigenvalues and eigenvectors. I can split terms and collect terms and get this very simple expression that that matrix exponential e to the matrix A times time is a matrix I know times a really easy diagonal exponential matrix times another matrix I know. I can compute all three of these terms very, very easily, whereas I could not compute all of these infinitely many terms easily. So this is much, much nicer. Okay, one last thing I want to show you, this is kind of, for me, one of the highlights of this lecture, is now we're going to interpret this expression, this solution. So this is a big deal. This is the solution. We're going to interpret this step by step, okay? So this T inverse times x naught, T inverse times x naught is literally z naught. So this term here is z naught. So essentially what we're doing is we are taking our initial conditions in the x coordinate system, in my original coordinate system that I wrote down my dynamics in my original x coordinate system for some reason. I must have had a good reason. So now what I'm going to do is I'm going to take my initial conditions, I'm going to map them through T inverse into a set of initial conditions in my nice z coordinate system. So this is, I'm writing my initial conditions in z coordinates. Then what I'm doing is I'm multiplying by e to the matrix dt. So this whole thing, e to the diagonal matrix d times time times z naught, this is literally z at some future time t. This is z of t. So what I've done is I've taken my initial condition, I've mapped it into z coordinates where it's easy to write down the solution. It's easy to write down z of t in these z coordinates. It's just, my initial condition times this diagonal matrix. That's z of t. So this is my solution in z coordinates, which is easy. And then finally, what I do is now I have the solution in z coordinates, but again, I wanted it in x coordinates in the first place. I started in x coordinates. And so to get back to x coordinates, I just multiply by big T. That's multiplied by big T, and now I'm back in x So now we're back to the solution in x coordinates. And I think this is just really, really cool. Like this for me is one of my favorite pictures in differential equations is this solution here and this real physical interpretation. These matrices T and D are not magic, okay? This is not eigenvalues and eigenvectors don't come out of nowhere. They are very, very simple and intuitive matrices that are useful for solving systems of differential equations. The T inverse matrix maps me from x coordinates into z coordinates, my initial condition x naught into z naught. In those z coordinates, my dynamics are diagonal. This diagonal matrix are my eigenvalues of my A matrix. And so it's easy to write e to the dt to solve, to move z naught forward in time to z at some future time. And then to go back to my original coordinates, I just multiply by t again. So very, very intuitive, very, very kind of simple in terms of eigenvectors and eigenvalues, how you solve x of t. Okay. Good. That was it. That was a big lecture. I'm ready to go home now. In the next lectures, we're going to look at specific A matrices that have certain structure, that have really interesting eigenvalues and eigenvectors. So for example, when these eigenvectors are purely real and negative, this will be a stable system. When they're purely real and positive, it'll be an unstable system. When they are imaginary, I'll have a rotating system, you know, kind of oscillating system, cosines and sines. And I'm going to build up all of your intuition for these systems of differential equations, for the whole menagerie of ordinary differential equations you can have in terms of these eigenvalues and eigenvectors. This is the new language we're going to use to understand these systems of equations. Okay, that's all coming up soon. Thank you.